Okay, it's 10:30 and we're starting on time because that's how we do it in commissioning. I'm delighted to be with you today. Today we're focused in this session on, I'm going to go through what we call system integration, which is just putting the pieces together. And then that's hard, but then making it all work harder. And we're going to hear from many members of the team that have got us to the point that you have data to look at. I'm very grateful to them, and I'm looking forward to hearing from them. Okay, in theory, my slides are there.
Okay, I found this on the web for my slides.
All right, so my name is Kevin Real. I am the observatory scientist for Rubin Observatory. I live in Chile. I've been there for 6 years. We planned on 2. That's how it goes sometimes. And I'm mostly going to focus on just the last year because the last year has been a pretty exciting time in Chile. I've been working on this project for a long time. One of my first jobs was in the Sloan camera. If you put in the G filter, the cosmic ray rate went up by a factor of 2. That's not real. So we wanted to make sure nothing was radioactive. This is me making sure Sarah Pachone was not radioactive. It's not. This is a tunnel. I love this tunnel. This is the tunnel at the just past the dam that takes you to the observatory, Poclaro Dam. And when we bring up 8.4 meter class stuff, this is what the tunnel looks like. Obviously, we have police escorts and shut down the highway because nothing else is getting through that tunnel. Well, this is the coating chamber, the bottom of the coating chamber. And so I've just got a bunch of videos of exciting events over the last few years. The first couple are a little more antique. I'll skip through a lot of them. If you type into YouTube, Rubin plus whatever the title of my slide is, you'll find the videos we're looking at, most of them. And of this particular install, my favorite part was the spaceship, which is here. The top ring of the telescope, when that went in, was pretty awesome. We have photos from every angle of this. It was pretty exciting. And that's the piece going in 2021. And then sneak peek into the future. This was from National Geographic, just around first look. And you could see the top ring of the telescope, plus, you know, the stars and the galaxies and all the cool stuff. This was us during our initial testing of our telescope. Our telescope is currently moving slower than this because we don't want to break our mirror. It's just a preference that we have. And we'll be able to go this fast again soon as we stop focusing on other things and focus on this again. But essentially, this telescope can just haul. And when it's just a big yellow cross, like it is in this video, a big piece of steel, you don't care, and you just make it move. All right, so what I really want to just take you through is really the minimal system that you need to take data on the sky. And we, as a project, really focused on this portion of things so that we get on sky just as soon as possible. And other things actually got delayed because we prioritized getting some data into the hands of the community. And so to do the science that we do, you need a telescope that moves and tracks the sky. You need a dome that opens and tracks the sky. And then you need 3 mirrors and 3 lenses and a focal plane. And so it's pretty simple. To make our telescope stop moving after we move really fast, making a short telescope was important. So our mirror number 1 and mirror number 3 are the same piece of glass. And so over the last maybe 15 or 16 months, this was just over a year ago, April of 2024, and we are coating our primary tertiary mirror. It looked like that for a little while. It was covered in a blue coating to keep it safe before that. We stripped that off and we coated. I'm actually going to fast forward on this a little bit. Again, you can see this on YouTube. But we make plasma and then we spin around and deposit that plasma on the glass. And then after you do that for a while, it comes out and it's beautiful. And so this was just over a year ago. So the last year plus a bit has been pretty exciting. The next piece that we put into place, the camera came to Chile right after we coded, and that was not by accident. We could not have a camera arrive while we were in the middle of coding. So there was time for one right after another. This is the camera at SLAC National Accelerator Lab in California, getting ready to come to Chile. I worked on the camera team for many, many years, starting in maybe 2011, maybe 2010. And this is us loading it into a container and then onto trucks. This particular portion of things was pretty exciting for me personally because I'd worked on this shipping plan for almost a decade before it happened. This is video taken by Travis Lang, our head engineer, sitting in the cockpit as we landed the aircraft that we had chartered. And if you look right here, the red truck at the very back, that's me. And so it made its way up the mountain and to the summit. One of the fun things was there was a trucker strike just that weekend. We were wondering how we should manage it. But Alejandra, head of ORO, just made a phone call. And we had motorcycle police escort us through Santiago and then police cars take us all the way to the mountain, which was pretty fun. And then the picture on the right is one of my favorite pictures of all time. It's Margot Lopez sitting in the cockpit for takeoff. Margot started working on the camera shipping plan with me maybe 2016. In 2018, she presented it to the DOE saying, this is how we want to spend the dollars to get the camera there safely. And then, 6 years later, actually made it happen. There's some delays in between there. I can't remember why. Shortly after that, we installed mirror number 2, already coded for a long time, onto the telescope. And here you can see us taking the safety cover off and exposing the glass. You can see the yellow cross that is the mass simulator in the reflection, and then the baffle going around M2. So we've now got our first piece of that minimal system. Then we put ComCam back on. It had been on for a while, but we hadn't been on sky with it. This is my favorite view in all of Chile. We open up the doors to the P-flow and it's Chilean Andes on 3 sides, and then the dome on the 4th side. In a minute, you'll see the camera being installed. It looks exactly like this, so I'll probably skip it just to save time. But we have about a centimeter of clearance from the side of the camera to mirror number 2 as that goes in. So obviously the planning is pretty intense. And it takes a full day to install that. Then in October of 2024, M1M3, the last of the optics went onto the telescope. And shortly after, so this is the coated mirror on level 3. It's on railroad tracks. You can see it rolling into the P-flow lift. And then there's equivalent railroad tracks on level 8 to roll it under the telescope. It's pretty, but you can see that without me telling you. Oh, here you can see the P-flow at the top with three sides, Chilean Andes. Railroad tracks in the dome floor, rolling it underneath the telescope now. And then right after the mirror went on, we had a full optical system and we went on sky with ComCam. That was pretty exciting. We had our first photon for ComCam. People dialed in on Zoom. There's maybe 25 people. I knew all of them, so I could actually share my screen and show people what was happening. First photon for Ellis's TCAM was not the same. There's about 250 people on Zoom. And I was in the other room while everybody was seeing cool stuff. I was trying to tell everybody in the other room what was happening. And I'm like, oh, they're cheering. I'll be right back, is what I said to the people on Zoom. This is a picture, I think, taken by Will on the night of first photon with ComCam. And then start of January of 2025, we start prepping for Ellis's TCAM to go on to the telescope. As I promised you, it looks awfully the same. I'm up here on that platform right there. minding my own business. And first photon. I ran into the room right after the picture because I heard them cheering. But it was a pretty exciting time. And that's it from me. I just wanted to show you some pretty pictures. It's been a really, really fun year and a half getting us from a whole bunch of pieces to on Sky. I'm confident that people here are pretty excited to be on Sky. And now I'm delighted to let you hear from the people making it actually happen. So, Marina. I'm happy to answer questions.
I have a microphone. If you have questions, Kevin might have answers. If they're wrong, I'll correct him.
I'll be around. All right. Thank you.
Okay. Oh, it's so strange. All right. Thank you. So I'm Marina Pavlovic. I'm commissioning scientist, and thanks to Bruno Heyun and Kevin who helped me make this presentation. They're not here with us today, but I think they're on Zoom. And Kevin also took like a half of my presentation, so it's gonna be a little bit faster. Okay, so today I'm going to tell you exactly the same story as Kevin told you, but I'm gonna add a little bit more details, and I'm gonna talk a little bit more of all the things that did not work during the integration and testing and commissioning. And all the things that we as a scientist do at Rubin Observatory that nobody ever tell you that you are going to do. So, oh, good. So I'm gonna start in 2021 when we started the first major testing and first major integration and go through not everything that we do, but like the most interesting parts that we did until today for the first photon and commissioning. So everything started in level 3 in the Rubin Observatory. I love level 3. I'm emotionally attached to this level because I spent most of my time on level 3. And that is the maintenance level in Rubin Observatory. Here you can also, all the equipment that comes to Rubin Observatory actually comes to level 3. So here you can see M1, M3. And from now on, I'm gonna call the primary and tertiary mirror M1, M3. You can see the commissioning camera on this side, and behind the commissioning camera is the secondary mirror, or M2. So all the equipment comes there, and then we need to figure it out how to move it from level 3 to level 8 and install it on the telescope. So for everyone that was never in the Rubin Observatory, this is how it looks from the inside. And this huge room in the middle, it's actually the level 3 or the maintenance room in the Rubin building. All right, so in 2021, we started the first testings of the subsystems of the telescope. I was not there, but this is one of my favorite videos that I have ever seen from Rubin. So on this side, you can see Doug Neal actually walking on, not on the mirror, of course, but he's walking on the M1, M3 surrogate. And we are actually testing the support system of the mirror. So we are testing the force actuators that we have inside of the mirror. So you can see like live force distribution as Doug is walking on the mirror. I'm so sad that I was not there that day. Again, we did a lot of testing with the commissioning camera. So this is commissioning camera, but this blue part that you see, Rubin blue part at the back of the commissioning camera, that is actually a top end assembly. And one day that is going to become a part of the LSST camera, as you are going to see. So we did a lot of testing with the ComCam on level 3, with a camera hexapod, with a rotator, and with a camera cable wrap. I'm not gonna talk about this a lot because I'm gonna talk more about testing with the LSST camera after this. So before August 2022, our telescope looked a lot different than it looks now. So you can see this is before August 2022. So you can see this yellow cross, that is actually a mass simulator. for the M1, M3. We also see a mass simulator for the camera in the middle. And this white thing is actually a mass simulator for the M2 mirror. So in this part, we did a lot of testings with the telescope mount itself, a lot of movements. And in 2022, August 2022, for the first time ever, we installed the commissioning camera on the telescope and did again all the testings with the TMA. So I'm not gonna tell you everything about the testings, but some of them, the most important one were, for example, the soak test. And that is pretty much mimicking the movement of the telescope through the operation. So it is an 8-hour of testing. We did some different movement as well, like serpent walk or random walk. But the interesting thing is that all of these tests that we did at that point, we moved the telescope using just one Python script. So for example, for the serpent walk test, we had a Python script with just 2 for, moving the telescope. Amazing. So this is the video that Kevin spoiled for my presentation. Thank you very much, Kevin. So this is how it actually looks like, all of these tests. I'm just gonna play it again because it's very cool. I was also not there for these tests, and it is amazing how big thing is moving this fast. And this is not a time lapse. This is actually moving of the telescope. It's moving like 70% of the maximum speed. We are still not moving it this fast. As Kevin said, we don't want to break the mirrors. But one day we are gonna come to that. All of these tests were not really smooth. Yes, Kevin? Yes, sure, of course. Don't worry, I'm gonna let you know if we plan to break the mirror. So none of that was actually very smooth. At that point, nothing worked. And one of the things that didn't work was DOM. So we had pretty much zero remote control of the DOM. So you can see here, Bruno Quinn, he is also a commissioning scientist, and he was manually opening the DOM shutter. Yeah, he described that as a full workout. I don't know, I suppose that some of the people who are here also did that manually. I didn't. Yeah, David, how was it? Yes, so Bruno said that they needed like an hour and a half to open just half of the DOM shutter. So it is like 3 hours of opening and closing the DOM during the day or during the night. So good thing that we did not have mirrors at that point on the telescope. After that, in 2023, we installed the surrogates and we started a final testing with the TMA before actually installing all the big important parts here. Kevin already talked about that. In April 2024, we had a huge milestone. So the M1, M3 arrived at the Rubin facility. We coated, and finally we had a mirror. This is one of my favorite pictures of the mirror after the coating. The second biggest one is the camera arriving in May 2024. That had a lot more problems that Kevin told. So yeah, it was a strike in Santiago that day. But also the truck that was supposed to move the camera from La Serena to Cerro Pachon did not have 4x4 drive. And in the middle of the transport, they needed to change the truck. I also heard that some of us lost our phones. Kevin, did you ever find your phone? Is it the same? Yeah, so a lot of problems, a lot of teamwork, but we actually get the camera on Cerro Pachon and eventually on the telescope. 2024 was a very important year. We had one more huge milestone. I finally arrived at Cerro Pachon. My plan was to volunteer for 3 months, and now a year and a half later, I'm still there. After that, we started actually installing the optics on the telescope. So first of them was the M2. This is very confusing picture. So M2 is up there. We have the light buffle. The camera is going through this hole in between and through the M2. And these black things are also light buffers on the telescope. And in July 2024, we installed the M1, M3. I'm not gonna stay here for a long time, but I think that I arrived in a really nice time in Rubin Observatory. And all of that brings us to the actual first photon with a commissioning camera. Commissioning camera and the whole 6 weeks was like, I would say, the most intense 6 weeks that we ever had in Rubin Observatory. It was stressful. We didn't sleep. We didn't eat. Telescope didn't work. We had some pretty nice pictures, but that was very nice because we did so much troubleshooting and we made our life with LSST cam much, much easier because we had this 6 week, not just with the system, but also with the software itself. After the commissioning camera was down and off sky, we started actual testing with the LSST camera, also on level 3. So before that, LSST camera was in the clean room, and then we finally put it on level 3. It was ready to go out. And I'm not gonna go through all of the testings, just some of them. So my favorite testings we did with the LSST cam on level 3 are the testings with the camera hexapod and the rotator. So we were pretty much pushing the rotator and the hexapods in all directions to see how they're going to respond. And we were testing the telemetry. Here you can see these plots of the movement of the hexapod we did. We were following the torques inside of the camera cable wrap, also the positions of the rotator. Of course, that didn't go very smoothly as anything we did in the commissioning. So for example, on this picture here, you can see me preparing to put my hand inside of the pancake wrap on the back of the camera because we lost a screw inside of the camera. That was not the first time. Unfortunately, not the last time. So we lose like 4 hours trying to take out the screw because it is very tight space and you have to move your hand inside with a little magnet and acting like a surgeon and taking off the screw from the camera. I did not take it off. It was Sean McBride in the end, but we all try. And here, for example, you can see Sean McBride. That was his bed for a couple of days on level 3. And he was literally looking at the camera cable wrap limit switches while we were moving the rotator. So yeah, and again, everything was moved with just one Python script. And of course, it didn't work. So we had to move it again. We had to change the Python script. And yeah, a lot of days of testing. Some of my favorite tests, and everybody here who knows me knows that I love the dome. I know our telescope is great. I know our camera is the biggest one, the greatest one ever, but I love the dome. The dome is my baby. So we did, again, a lot of testings with the dome. We did, again, a soak test that is mimicking the movement of the dome. We were following the dome motor's temperatures all the time to see how they are going to react. Here you can see some results from the soak test. We did also something called a cadence test. That is moving the dome with a long slew and then crawling to another position, like very, very slow movements. And we were testing if dome is going to stop when we needed to stop. It didn't. And we were again following the dome motor's temperatures. How it actually looks like, it was 6 in the morning. It was 6 degrees inside of the dome. I think the coldest day that I have ever had in the dome. I had 2 Rubin jackets on me. We didn't sleep, we didn't eat at that point. We wanted to finish the test before the day crew arrives and wanted to do their testings. So it was David San Martin with me. And after this test, we had to go down to La Serena to get some sun. That was a mistake, it was cloudy. And those are the pictures with the infrared camera. David had an infrared camera, and we were trying to see if the actual temperatures on the dome motors are the same that we are getting from the telemetry. Very interesting day. And finally, all of that brings us to installing the LSST camera on the telescope. Is the same video that Kevin showed you. And we thought we were ready. This is the 15th of April, 2024, the day of the first photon. We thought we are ready, but not really. That day, we had to do so many tasks. And all of these tasks actually demands a whole day of work. For example, we had to do a filter swap. So we had to put the filter inside of the camera. Now we have like a whole day when we have to do a filter swap. In that moment, that was like, oh, a minor thing. We just have to put a filter in the camera. The other one was we needed to move the calibration screen. So it was in horizontal position before that. Now we needed to move it to look at the telescope. Then doing these dome tests days before, we blew some switches. So we needed to change them also. And there you can see electrical team changing the switches. We also needed to take out a part of the fence from the telescope itself. That is on this picture here. But when you take out anything from the telescope, that means that you're changing the mass. And if you change the mass, that means that you need to balance the telescope again. So again, we needed to balance the telescope. And all of these things are happening in the same time. So Freddie was balancing the telescope, and I was on the shift that day, and they called me for something called dome handover. And dome handover is something we do every day. So that is switching the dome from the manual control, from the engineering mode to remote control. That procedure it has a lot of steps, and you can make mistakes in all of these steps. And all of these people are inside the dome. And besides all of these people inside the dome, we have media crew, we have visitors, we have Željko there. Everybody's there, and everybody wants to see the dome moving and the dome handover. So everybody can come with me. And in all of these steps, I made a mistake, and I stuck the dome an hour and a half before the first photon. And then I hear Freddie running on the telescope. And I'm like, Freddie, what's happening? And he said, I stuck the telescope. I'm taking the radio, calling Brian. Because when nothing works, you call Brian. And I'm like, Brian, what should I do? Well, you need to call Željko and tell him that we're not going on Sky. And we have Victor on Zoom with 250 people, 2 hours before going on Sky. Telescope stuck, dome is stuck. And the media crew is asking you, oh, are you excited? Yeah, of course, sure. But we had a lot of help from the people from Italy, from Tiago. Tiago, I think you're there. Yeah, thank you very much. And we managed to unstuck the dome and unstuck the telescope and come to the first photon. And that's why I'm that excited. It's not for the first photon. I'm like, oh my God, the dome is moving. Of course, commissioning didn't stop there. We had a list of things that we need to make it work better. We need to understand it better. We have planned for all of this, don't worry. We are on track, but it is a really exciting time because sometimes you find yourself, one day you find yourself inside of the M1, M3 mirror. One day you find yourself on top of the camera. One day you are painting the screws because they're making a stray light on your pictures. So all the things that scientists don't realize that we are gonna do that in the commissioning phase. And this here is just a plan for the improvement of the dome. So all of this have to be done in the dome. I'm not gonna talk about that. It's like the whole other talk. And with all of that, we are in the winter. We have some very bad weather. And sometimes the day after the bad weather, we have to go up on top of the dome and inspect the dome if there is any snow or ice there. So that's me on top of the dome. And even though this presentation and this talk look like, okay, a lot of problems, a lot of struggles, a lot of things that doesn't work, those are one of the happiest moments that I have ever had in Rubin Observatory. And I have to say, thank you very much. Thank you for the whole team that made it happen. Thank you.
How did you unstick the dome?
Tiago's magic. So no, in the end, we pretty much restarted the part. It lost the connection with the software, so we had to reboot that part. And that is something that happens. It's not something that happened only that day, but it's not a really good moment to do it when everything is going wrong. So yeah.
We told her not to mention the sledgehammer.
There is a question.
Thanks for a great talk. In both talks, we heard that you want to make sure that you don't break the mirror when you move the telescope too fast. So how do you like at some point you have to move the telescope very fast with the mirrors, right? How do you make sure that you are certain that you will not break the mirrors? Like, what are the kind of things that you look at?
Yeah, thank you. That's a great question. So we are moving it slow, and then we are going faster and faster and faster, and we are changing the movement of the telescope, and we are tracking the forces that the system, that the force actuators actually experience. So there are limits. After some forces, you cannot go faster, or you cannot go in that direction anymore, or you have to change the way you're moving the telescope. So it's pretty much following how the force balance system is actually responding to the movements that we are doing.
What type of tests went into the actual transport of the camera? So Kevin, you had mentioned that there was a lot of engineering and many years that went into this, but what were the type of tests that led up to it? Did you put like a big brick inside a box?
We built it. We had a full scale mass simulator of the camera, put it on the shipping container, drove it around the Bay Area. I mean, all kinds of things, really. It was one of these, should we spend another week doing that? Yeah, we should. Should we build this thing to make sure it's safe? Yeah, we should. So yeah, everything you could think of, we did. I mean, we had something called a failure mode engineering and analysis that we went through, everything that could go wrong, including things like not literally a trucker strike, but some reason we couldn't go from Santiago to, so we'd already established where we would store the camera safely, but nobody wanted us to store the camera safely in Santiago. They wanted it on the mountain. So we got a police escort. And so really, Margot especially just spent countless hours thinking of everything and testing everything. And it was, other than a few things, it was totally smooth. Okay, we should move on.
Hi everyone, I am Kshitija Kirkar, or commonly known here as Kiki, and I am an observing specialist with Rubin.
And hi everyone, my name is Kate Napier. I'm also an observing specialist, whereas Kshitija was hired through Aura. I'm a SLAC observing specialist, which is slightly different. I have the majority of my time spent to support observing activities, and then 20% of my time is spent on research in the first 2 years in Chile. And then after the 2 years is up, I'm going to go to SLAC, where my responsibilities are swapped. The observing team at Rubin is comprised of both observing specialists as well as commissioning scientists. Currently, we have 15 observing specialists on our team representing 8 different countries from around the world. And next week, that'll increase to 16 observing specialists from 9 different countries. And all observing specialists are based in Chile. And the other part of the observing team is the commissioning scientists. There are 11 commissioning scientists representing 4 different countries from the world. And the commissioning scientists are split between Chile. Some of them live in Chile and some of them live in the United States. Here on the left, the observing team was one of 2 recipients of the Rubin Team Award earlier this year. So here's part of our team photographed at the award ceremony. And then on the right is a portion of our team at the First Look event in La Serena. Okay, so you heard from Marina a little bit about the role of the commissioning scientist, but in terms of the observing specialist, all of this cool science that you've been talking about all week, all of those images were taken by our team. So it's a pretty cool team to be a part of. This is our mission statement. The observing specialist team is a diverse group of people driven by excitement for discovery. We aim to guide photons from the farthest reaches of space and time and assist to transform them into precise and detailed data that expands human knowledge, contributing to the largest library of astronomical data ever built. I've heard a few questions from you all this week about what our shift schedule is like working at the observatory, so I wanted to spend a little bit of time talking about that. Us observing specialists, we work either 4 days or 4 nights at the summit. So work takes us up from La Serena to Cerro Pachon, which is about an hour-and-a-half drive. And we stay there at the hotel and work either during the day or during the night. So at any given time, there are 4 observing specialists at the summit. 2 work in the daytime role, that's 10 a.m. to 10 p.m. And then the other 2 work from 8 p.m. to about 7 or 8 in the morning. And during each of these shifts, one of the 2 observing specialists is designated as the shift manager. So they're the ones kind of with the ultimate authority at the summit. And then commissioning scientists over the past few months have been working with us at the summit Monday through Thursday during the daytime. And then they support us in a remote capacity during the nighttime as well as on the weekends. And commissioning scientists also take on different roles as well. They serve as the night planner, so they kind of organize all of the tasks for each night and communicate that to the rest of the team. And as we shift into more of the operations phase of the project, the camera team has really been starting to transfer a lot of their knowledge to the commissioning scientist. And then, like I said, they support us both at the summit and in a remote capacity. So we are really busy almost 24 hours a day, 7 days a week at the observatory. And the goal of the daytime activities is to prepare both the Simone Survey Telescope as well as the Auxiliary Telescope, or Auxtel, that sits on Calibration Hill right next door for nighttime observations. So here in purple, I'm just showing some of the daytime tasks that we're responsible for. So for example, once the observing specialists start at 10 a.m. each day, we're in close contact with the other teams at the summit, such as the mechanical engineering team, the electronics team, so that we can coordinate when it's safe to start our responsibilities. And for example, we want to check the health of the actuators and the hard points that support the M1, M3 mirror system. We also want to do a checkout of the telescope mount assembly to check that the slewing and tracking are working as anticipated. And then we heard a little bit about the dome handover from Marina earlier. So that's pictured in the top right here. So around 4:30 every day, the 2 observing specialists go up to level 7 of the observatory, and we're working with the engineering team to transfer the dome from manual control to remote control. So that involves like doing a test slew of the dome, testing the opening and closing of the shutters. And then as we proceed into late afternoon, once sunset happens, we're opening the dome, we're preparing to go on sky. So we run through what's called the Simone on sky checklist. And then before proceeding to any other observations for the night, we'll do an initial telescope alignment. And the goal really here is to minimize the active optic system residuals and hone the image quality. Then as we proceed to the early night, there's a 2-hour period of overlap between the daytime observing specialists and the nighttime observing specialists. And this is really for there to be continuity of observing and transfer any of the details from the daytime to the nighttime observing specialist. So during the night, we've now routinely been running the feature-based scheduler science validation surveys. So that takes up the majority of each night. But we also interleave other special test requests. These can come from the active optics system team, such as building observations for the lookup tables. And we also do a stray light test request. About a month ago, we started exercising the target of opportunity infrastructure. And we've heard today and yesterday that the target of opportunity is now successfully running at the summit with the first observations being taken. And then I know it's hard to imagine because we are like in almost 100-degree, 90 to 100-degree temperature here, but actually we're forecasted to get about 30 centimeters of snow at the summit today and tomorrow. So we do have contingency plans of closed dome test that we can run when it's unsafe to open the dome because it would put the telescope at risk, but it's still safe for staff to be at the summit. We'll run closed dome tests. Those could be dynamic testing, trying to move the TMA, the telescope mount assembly, at faster speeds, or they could be like examples of taking more calibrations. So, and then on the Oxtel side of things, we've, for the past month or so, we've been running the Simone survey telescope alongside the Oxtel. And Oxtel is really, the observations are driven by the scheduler, and it's pretty smooth sailing, so it requires pretty little intervention from us. And so the time lapse that was playing was just showing that, yeah, both telescopes are simultaneously observing at nighttime. And then the bottom right-hand figure is the calibration screen lit up in a combination of the 4 different LEDs. And now I'll pass it over to Kshitija to tell us more about the concept of operations.
Do I have time, Kevin? Oh, I have 2 minutes. Great. Okay, so our entire observatory is 3 minutes. Thank you, Kevin. The entire observatory is controlled by the observatory control system, and that controls the 4 major parts or components, which is basically our telescope, Simone survey telescope, our camera, the Oxtel, and the lattice, the DEM and the DREAM instruments, which basically give us an independent measure of the seeing and the atmospheric quantifiable measures that eventually go into our feature-based observations for the nighttime, and the calibrations and the entire environment system of the facility. We do this through what we call the commandable solve components, which are the lowest level controllable units that where through which a software can directly talk to the hardware. So they manage the telemetry data of each of the system, as well as they can perform actions that we command them to do. For more details, Tiago is going to discuss this tomorrow in his plenary talk. But how we actually command each and every components of a telescope, we do it through the service abstraction layer scripts, or the SOL scripts. So these are basically a compilation of a Python script which has the commands that we will be sending to the hardware component, like the mount or hexapod, etc. The configuration of how we want the command to be executed, and what the observers, us, execute is basically the SOL scripts. And these can basically be the officially supported SOL scripts, which are the scripts that we use frequently, regularly throughout our day and night operations, or under development SOL scripts because we are still in commissioning. So there are a lot of procedures and a lot of operations that we are still compiling. And it also includes some of the testing scripts that Marina and Kate expressed. And the scheduler block source, which are basically the scripts that our feature-based scheduler runs every night whenever we go on the sky. So we have had a lot of talk about all the fun things that we have been going through commissioning. So I will rapidly just go through this slide. Before our on-sky commissioning, the way we used to operate whatever components of telescope we were integrating through low-level GUI EUIs, Python scripts, coming up with temporary procedures which will keep changing every week, sometimes every day, and a whole lot of troubleshooting because we were still figuring out all our hardware components. During our on-sky commissioning, which is still now, most of the hardwares are now controlled through CSCs. We are started establishing standard procedures. We are defining standard scripts, which we will be continuously using, hopefully, through the entire duration of the survey. We are also developing new scripts because we want to be efficient, which we are not yet. David is going to talk about it in his talk. And our troubleshooting is kind of going down. Where we want to be once we are in early operations is basically have a good handle on the day and night operations protocols. For example, protocols for opening, the dome opening and closure conditions, managing environment, emergencies, etc. Improve observing efficiency, having standard and non-standard operating procedures, standard scripts where the scripts that we are still developing hopefully will eventually evolve into standard established scripts, full operations documentations that we will be delivering, and very minimal troubleshooting. And the general workflow of the operations on the summit over the 24 hours is basically we have teams, we have two teams of observing specialists and commissioning scientists. And the way we work is together. So because our roles are different, we keep continuously sharing information and working on feedback from each other. So currently where we are at is the observing specialist team has been handed over the control for most of the major components of a telescope and the observatory, like M1, M3, the top-end assembly, calibration system, the telescope mount assembly, and the dome. The observing specialists are, in return, are working on delivering our official documentation for operations. Currently, we are undergoing the process of being handed over the active optics system. And the commissioning scientists are working with the camera team and the filter exchange team to start the handover of the camera eventually to the operations and the observing team. And this, all of us, the superhumans who are behind the fantastic data that we have been seeing since our first look, and the science that you all have been producing with just the first release. So we have any questions? Let's see if there's any questions. Yeah.
And come see our Rubin nails up close too. We both got them done, so they're great.
And sorry, Marina, I didn't include your picture because you had a whole talk of your pictures.
We switched online.
Yes, yeah, it's Sean.
Hey, can everyone hear me? I think I heard a yes. Okay. Kevin, will you drive on my behalf?
I will.
Thank you very much. All right. Well, thank you very much for having me here, and my apologies for not being in person. I'm involved in, my name is Sean McBride. I'm involved in multiple facets of LSST and Rubin Observatory. But today I'd like to talk a little bit about the camera, the LSST camera, which I've been involved with for a little over a year now. So next slide, please. So the LSST camera, I just want to get everyone on the same page. We've been talking a lot about the photons that we all are very, very happy to see, but how do they actually get to the beautiful pictures that we've seen through first look and related to recent asteroid fields. So light comes in through the L1 and L2, the first two lenses of the camera, and it passes through what we call an auto changer. Now this auto changer holds one of our 5 loaded filters from our filter carousel. That selects light based on however the scheduler or our survey strategy demands. The next piece, optical element that light passes through is our camera shutter, which is all integrated inside of the camera body, which keeps the camera at a fairly stable thermal equilibrium. And the filter carousel sits on top of our cryostat, which is pumped down to 10⁻⁷ torr in order to keep the focal plane assembly and the electronics at a very, very low vacuum and very well thermally controlled. We keep our focal plane assembly cooled to about -100°C at the sensor level. And in the back of the camera, you'll note there is the quad box and utility trunk. This holds some of our electronics, power distribution units, and vacuum systems necessary to keep the cryostat at a constant level. Next slide, Kevin. So to give you an idea of what LSST cam looks like when you actually look at the pixels, this is one full LSST mosaic, and I've zoomed in on a 3x3 array that is the approximate size of the ComCam images in the ComCam field of view. If you go to the next slide, you can actually see what the first look images look like if you overlay them at that scale. And it's about 0.6 degrees on each edge here. So it's pretty impressive, the amount of detail that we're able to extract. Next slide, please. And so LSST camera has had a very exciting past year. We spent about 4 months of last year performing electro-optical testing at the summit. This was involving teams of 2 camera shifters, as we called it, running optical tests on the camera to make sure that it passed our post-shipment tests and also performing final optimizations to the focal plane. We then spent another 3 months performing mechanical tests on level 3, as Marina previously described, before acquiring first photon on April 15th of this year. Now, there's lots of discussion related to these tests before, and I've linked them in this presentation, but I'm just going to focus on the testing that has happened since first photon on April 15th. Go to the next slide, if you like. The first test that we did on the night of first photon was evaluating our sensitivity to bright stars. So during this electro-optical testing period of late last year, we identified some sensitive readout electronics boards, or as we call them, REBs. These REBs were sensitive due to higher than normal currents, causing the high voltage that we normally apply to the CCDs to be tripped by our safety limits. Now that high voltage is about 120 microamps, and you can see in the bottom right plot, in one of our highest brightness exposures that we acquired on first photon night, we were still very clear of this limit. So we were able to establish that we were safe to observe, obviously not staring at the moon anytime soon, but we're not worried about bright stars having any damage, causing any damage to the focal plane assembly at all. Next slide, please. An additional test that we took in the following weeks after first photon was evaluating the repeatability of our filter changer system. We established a requirement of about 10 pixels or 100 microns, and we took different exposures using the collimated beam projector, different masks and different rotator angles. And we performed a difference image analysis that showed we are well within our specification. We only noted a maximum difference in filter repeatability of about 68 microns, where our specification was 100. So this was one place where we were able to safely satisfy a system requirement. Next slide, please. So as you've probably heard potentially elsewhere, but maybe this is the first time, when we acquired first photon, we did not have every sensor powered on at the time. And so we started first photon with 199 of our 205 sensors. And there were 2 separate issues we had to encounter. And one thing to keep in mind is that our REBs, or readout electronics boards, they're multiplexed through 3 CCDs at a time. So when you're powering on CCDs, you power them on in batches on each REB. So if one CCD goes out, we had to deal with all 3 at a time. So the first was in this location that's highlighted in red here. We had a faulty reading due to an analog digital converter, and this blocked our power on sequence because it identified it as a safety issue. Now, While this was frustrating, I actually want to highlight that this is a benefit of the sustained development of the camera control system software, that it was being safe in this instance and preventing us from turning on these CCDs. Now, we were able to recover them through minor modifications to this code a little over 10 days later. So this is actually first photon for these CCDs with the LSST camera attached to SMONI telescope. Next slide, please. And we had one other issue related to CCDs. Now, we identified during early slews of the telescope mount assembly and a likely identical electrical short on one readout electronics board. And this affected 3 CCDs. We quickly stopped to assess the issue because electrical shorts are some of the more dangerous kinds of electrical optical failures that we can experience on the focal plane. But after some modifications to our camera control system code, we were able to turn on 2 of the 3 CCDs on this REB, and those are highlighted here in red. The one CCD where we suspect the short is, I've highlighted here in blue, and we have no plans to turn on this remaining CCD. So we're planning to continue with 204 out of 205 sensors, or exactly 99.5% of the entire focal plane. Next slide, please. We've been continuously making optimizations to the focal plane, one of which is what we call idle clear. This keeps the sensors clear from latent charge that hangs around on the focal plane and prevents us from tripping off our high voltage. We had disabled it previously due to it introducing thermal fluctuations on the focal plane, but we modified that idle clear sequence and have re-implemented it to LSST cam in early July. So now the focal plane is in a very safe state due to the implementation of idle clear. Next slide, please. We've also improved what we call our sequencer. Our sequencer is responsible for reading out the camera according to a set of rules and procedures. These improvements have resulted in decreased noise in many of our sensors and decreased signal correlations, which is really, really important for us. Now, we've noted that these sequencer improvements do show some readings of increased noise across the camera and a very, very minute increase in charge transfer inefficiency, but overall, these have been a positive change to the camera configuration. Next slide, please. One of the subsystems I mentioned earlier is the camera shutter. And we have identified very early in our LSST cam on Sky campaign, a timing offset, which came in the form of our motion fitting algorithm. And so we had to adjust our timing and peer-to-peer communication settings in order to make sure that our motion fitting algorithm was not experiencing a significant timing offset. Additionally, we've been evaluating the shutter belt and the actual belt that does the pulling and pushing of the shutter blades as they move across the focal plane. And our preliminary analysis shows that there's been minimal impact on the belt lifetime, but this is still ongoing. And I'd like to note that we've almost crossed 50,000 shutter actuations, the single camera shutter one that we've been running. So it's been very, very effective so far. Next slide, please. In the remaining 2 minutes, I'd just like to highlight 2 things that we're still, 2 subsystems that we're still trying to improve. The first is our filter exchange system, which has actually been performing quite adequately. We've had continuous filter changes since first photon, and we've been swapping our filters on the regular 2-week cadence according to the moon. We've had minor errors during filter changes, but most of them have been a straightforward recovery for our filter exchange experts who reside in France, which is actually quite convenient for us since morning in France is middle of the night in Chile. Next slide, please. However, last week, we experienced our first major hiccup related to the filter exchange system, where one of the 2 clamps that moves the auto changer was sensing the filter it was trying to load into the camera, while the other sensor was not. We have since removed the individual filter from the camera and inspected it. There's no visible damage to the optical surface of the filter, so rest assured that is okay. But we're still having discussions about how to best optimize the survey cadence, given that we, as of right now, cannot use that socket in the filter exchange system. And so that's a conversation that's happening at the operations and survey strategy level. Next slide. Finally, I mentioned briefly at the beginning our cryostat, which is responsible for keeping the camera sensors cool. And since we powered on the cryostat and went through our first cool down at the beginning of April, we've had the longest continuous run of our cryo systems, which is a massive win. We've had to make frequent additions to the cryo circuits in order to keep them performing smoothly. And we had 2 of our 6 cryo circuits had individual issues that we had to identify and fix throughout their regular operation. And so now we have all 6 running and working optimally. Next slide, please. And while all 6 circuits are running, we've identified a sensitivity to ambient temperature in the dome. Now, whenever we experience ambient temperatures of air temperatures below 7 degrees Celsius, we start to see a decrease in cooling efficiency. This is a big problem given that it's the Chilean winter. We have several hypotheses for these, but regardless of the hypothesis, we have different mitigations ongoing, including insulation, heaters inside the dome, and heater tape itself installed on the cryo lines. As of right now, this is one of our most disruptive factors for observing, and one of the factors that we're trying to address as soon as possible, especially given that Chilean winter is set to conclude fairly soon. Next slide, please. And so I'd just like to conclude that the camera team has worked incredibly hard to bring the camera to the position that it is today. However, we're not finished optimizing the camera. We still have many, many things that we can do in order to make sure that the data that you, the community, obtains is of the highest quality possible. So we're going to continue to work as we transition through science validation into the LSST survey. And one last thing, I'd like to just thank the entire camera team who's made it possible. There's about 10 people in this photo here, but it's hundreds of people across many, many continents who have brought the LSST camera to fruition, operating efficiently and smoothly at the summit. Thank you very much, and I'm more than willing to take questions.
We do not have time for questions, but we'll take one anyhow, if somebody has one.
Yeah, so regarding this one, that sensor, will there be opportunity during the next 10 years to fix that, or not at all? We'll just live with that.
We have no plans to turn that sensor back on. At the current state, we assess that there's more risk to the rest of the focal plane by trying to turn it back on than leaving it off. So it's a minimal impact in terms of pixel loss. We're only losing about 0.5% of the focal plane. We plan to keep it off. If a eureka moment comes to us and we deem it safe, I think we can open that conversation. But as of right now, there's no plans to do that.
Right, thanks.
And you'd lose 5 to 10% of the survey changing out that one sensor. So make the trade.
Need to die before you kind of decide we need some corrective action.
Right. I mean, and if it is a short and that short somehow disappears, we'll notice and then we'll have a conversation.
Yeah.
I think Keith, are you next? Oh, David's next.
It's
Great.
David.
Where is the presentation here? Oh, it's here. No. No, it's not. It's... No. Now you can maximize. All right. My name is David San Martin. I'm also a commissioning scientist. I'm based in Chile. I have been living in Chile actually now for 11 years already. My original plan was going to Chile, stay there a year, learn everything about telescopes, go back home and continue my career. So I still didn't learn everything, so I'm still in Chile. So this is going to be kind of a continuation of what's presented by our observing specialist team. I want to tell a bit how we have improved our efficiency. For example, to go in sky, how we can recover better to do not lose time during the night, and what we have been doing to improve this our efficiency, so we can keep acquiring our data. I always like to read again the Rubin mission statement because I find it's very beautifully written. It's also super powerful, and I also like to remind myself that my main job is to make sure that we understand well the system that will allow us to obtain all this amount of data that we are planning to do. So as we are now in the final stretch of the commissioning, and since we have accumulated a good knowledge of the system, we think not only as individuals, most of the team has a good knowledge about the system. They know how to operate the system in a very not only automated way, but if it's manual intervention needed, they know how to do. So it's time to improve our efficiency then, because we understand the system. We have removed a lot of blockers that we had in the past with some systems that were preventing us to go to improve our efficiency. That what is more or less the history of the campaign of the commissioning camera. So every minute that we save, every error that we prevent will has at the end impact in the community. So going back to the commissioning camera on Sky campaign, as Kate was saying, it was, and Kishita was saying, it was a very demanding campaign. It was a difficult campaign. The system, people, I mean, our team was not we were not well trained as we are right now. That's one thing. But also the system was not performing as always as it is right now. So we learned a lot from that campaign, and we collected several improvements requests that we needed. We could identify as a team things that were blocking us, things that we need to improve, and make some prioritization of those requests. So here we have just a part of a documentation with those requests. We can see status, what would gain. For example, here, well, we cannot see there, but there is like, say, estimated time, how much time we would save if we improve that system. And then we collected all those requests. It's a big list. Here I just show some of them. Some of them would like, some of the procedures that we're doing during the day to prepare our system, they were taking very long time. For example, the health checks that we do for the mirror with the actuators and with the hard points that guarantee that the mirror is safe, that we are not going to break the mirror. That was only taking 2.5 hours more or less every day. And we have other blockers, for example, the dome shutter. The dome shutter at that time, during the commissioning camera campaign, it was operated not remotely. We had to go up, press buttons every day. So we are losing a lot of time with this. So we collected this big list. I am not going to talk about each of those points, but each of those points, here we have more. So the list of requests was kind of extensive. Here I have at least more or less 20 different requests. And each of those were a pain point and some point. Each of those bullets represent some inefficiency in the system, something we need to improve, or not only inefficiency, but a point of a failure, something that can prevent us of going in sky or can take time from sky or from preparation. So those requests, they were not at the beginning, they were requested for different people in the group. So they were not they didn't come organized to us. So we kind of organized those requests in a workflow that makes sense because some of those requests had overlap with other requests. So we had to organize those in a workflow for our daytime preparation. Here, I do not expect that you will be able to read. That was not the idea. It's just to show you the workflow that organize part of those requests that are related to the preparation of the system or during the night. Here I show half of that workflow that maybe you can read a little, you can see better, you can read a little. I only have 5 minutes. Oh God. All right, so I'll jump this. Well, here you can see those requests. Some of them you can see that have those green checks. It means that we have this in place. For example, we have now a script to unpark TMA that was a very, not complicated, but time-demanding, consuming process. Here you can see others that we still don't have. If you don't see the check marks, it means it's not available. Or if you see this little box up, it means that we have a ticket, that we are working on it, that is in preparation. Moving forward, so even though we had this big list of requests, we also have after the maybe 80 months more or less, we have also a big list of checks. So we have accomplished a lot of what we have planned. Here I have maybe out of 10, we have 8 of them already in place. For example, those here, they are the ones that are consuming a lot of time from the preparation. We are barely being able to go in Sky during the commissioning camera campaign in time because of those daily checks that we had to do every day. So only with this, we were able to save around 4 hours every day. But it's not only about saving time. For example, this one that I'm showing here at the end, this is a script. It's an automation that is, it does not save much time, maybe 5 minutes, 10 minutes at the end of the night, but it's at the end of the night. So we are not only concerned about saving time, but it's also, we are imposing less cognitive effort in our team at that time, and we also avoid mistakes. Well, there's another ones that we haven't checked yet. So we can see there's more with checks, others we don't. One here, I'm just pointing some of the automations that we are working right now. The first one is telescope and dome checkout. Then the camera checkout that we will every day take an image, or a couple of images. We'll check that the images are correctly ingested. We'll check that the pipelines are running. We can optionally exercise the filters of the camera. So it's not always about saving time. It's also about reliability, making tasks simpler, less error prone, and also making the procedures more robust. For example, maybe I have time to show this. This is the procedure when we are at the beginning. It was very manual. When we need to go in Sky, we have all those questions that we need to answer before going Sky every time, or when we recover from a fault to go back on Sky. And this was a very manual procedure. We had to go to our observing virtual environment that we call LOV. We would need to check, for example, that all those boxes here in the red squares were green. If they are not, then you need to take action. For example, for the other system, we need to go to the EFD, EFD means Engineering Facility Database. Then you go to the Engineering Facility Database, coronagraph interface. Then in the middle of those numbers, you identify which system you are looking for, what the status is. Oh, it's there. Then you go back. Then you go back to the observing virtual environment interface. You identify the script that you need because you know a lot about the system. You know which script you need. Then you run it, and then you repeat for all. Then that's a very time-consuming. It's not efficient. That's what we're operating in the past. We are, thanks to God, not doing anymore. So this is something not efficient. It's error-prone. There's a lot of problems. And after 10 hours shift, even worse. It's easy to make a mistake. And then you can lose a lot of time on Sky. So what I did, someone came with a great idea. that we need a script that would be called recovery TMA. We would recover everything for you, but that was not exactly how it ended. It ended as a script that we call ensuring sky readiness that will do for us. We'll check the engineering facility database. If the status is not the one that we need, we'll take action. It has been used in the past maybe 2 months. We have been, you can see in this column that in general take less than a minute after the recovery. The recovery may take longer, but to prepare the system to go in sky, in general, a minute, unless it has to take action like raising the mirror. But in general, when we start the night, we have already prepared the system. The mirror should be already raised. Most of the system should be ready. It's just like a check that we are very good. And right now we are still working on a couple of them. For example, the camera checkout, there is a pull request open, prepare for on sky, pull request open. We are just about to finish these ones. The other one with the Jira means that we have tickets for them, but we are still not working on them. Someone is now working the telescope and DOM checkout script, someone. And also anyone in the team can propose a new improvement. If you see something that's blocking us, it's a pain point, we have a workflow, we have documentation for this, we can check our workflow, identify the inefficiency on the pain point, we will formalize the request with a ticket. Someone will do the triage, we'll make a prioritization, we'll implement a script, or maybe escalate as a hardware improvement for engineering team or a policy that the G6 leads need to confirm that we are good to do. So anyone can propose. So ownership of the efficiency is distributed. It's transparent because you can check the status, what is existing, what is not there. And just for to close this, it has been a very busy time since the Concan campaign. But we believe now that we'll finish all those requests. Maybe when we start the operations, we are very close to this. And just finally, just to repeat again that the efficiency isn't just about doing things faster. It's also about doing things faster, but it's also about reducing the burden on the observing team and make sure that they can spend time not repeating tasks, but monitoring the system, checking the image quality, and things that make sense that our awesome team of observing team can spend their time, not with repetitive tasks. And even though we know that automation empowers the team, it's very good that they joined the project in a time that we are not so automated because they learn from the base how to do things more manually. I think this at the end was really, really good. And that's it. Commissioning continues and ongoing improvements are still essential. That's it.
Who wants the glory?
I'll just mention that David's efforts are awesome, making things way better.
One of our many Brazilians on the summit.
Okay, Keith, I think you're on last, correct?
Can you hear me okay?
Sounds great.
All right. Are you going to drive?
Yes.
Okay, then I'm ready for the first slide. Okay, hi everyone. This is Keith Bechtel. I'm a system verification validation scientist for Rubin Observatory Construction. This is a talk about the science validation surveys, the progress, the performance, and planning. Next slide, please. So there's an enormous amount of material to cover and not much time. So for the scope of this presentation, I'm going to focus just on the overall system performance characterization, looking at the first month of the science validation surveys. I put in a bunch of pointers to other material at the RCW and also a link to our weekly commissioning updates that give more of a play-by-play narrative of how the OnSky commissioning campaign has gone. We're going to be decreasing the cadence of those updates as we're transferring more and more information to our SV surveys progress pages. Next slide. So the big picture here is that Rubin Observatory, we're trying to do something that's never been done before. We're trying to achieve atmosphere limited image quality across a 3.5 degree field of view on an 8-meter class telescope. And we need to do this while rapidly scanning the sky under variable environmental conditions every night for 10 years. So it's not just about the capability, it's about basically directing 350,000 kilograms of glass and metal to hold the surface of the mirrors steady within about 10 nanometers precision, and doing that while constantly moving the telescope under all different environment conditions. Next slide. So just some nomenclature. LSST-CAM first photon, this refers to the first time that we have on-sky photons passing through the fully integrated optical system and being recorded on the camera. This took place on April 15th. System first light is a much more comprehensive technical achievement. That happens when we can routinely acquire acceptable science imaging across the full LSST-CAM focal plane while doing survey mode observations, and we have a well-understood technical path towards the construction completeness. So this requires retirement of the major technical risks, it requires reduced uncertainty on the remaining construction schedule, and it requires a shift to this emphasis of bulk data collection. So that system first light technical milestone was achieved in early July 2025 on schedule. We basically had a very detailed week by week schedule, and we've been able to hold that through the on-sky commissioning campaign. However, our on-sky commissioning and system optimization is still ongoing. Next slide. So this is a recap of LSST-CAM first photon. The image on the left is showing basically one of the detectors on the very first on-sky image. It was within about 3 millimeters of being an optical focus. This was a huge testament to all the integration work that had been done by the team leading up to being on sky. And within 15 minutes after a manual focus sweep, we were able to get the first PSFs that were under 2 arc seconds. Next slide. Within 3 nights after first photon, so by April 18th, we were able to run the AOS closed loop to convergence at a fixed location on the sky, and we could achieve a PSF full width half max of 0.7 arc seconds across the full focal plane. So already within a few nights, we knew that fundamentally the intrinsic capabilities of the system were on track to meet the LSST science goals, and it was going to be a matter of improving the consistency of performance. Next slide. So the stage we're in right now is that after spending 1 to 2 months of the on-sky campaign really being focused on specific observations of target fields, this is for commissioning the AOS closed loop system, for taking the observations for first look, for getting initial data sets for science pipelines commissioning. We were basically picking specific fields and staying on there and taking hundreds of visits at a time. What we're doing now is much more challenging. We're in the stage of running the science validation surveys, and we have to survey the sky in a continuous survey mode. And this is a full rehearsal of the observatory operations. So it requires the AOS closed loop and the open loop control systems functioning. It requires thermal control of all the different subsystems. It requires running the environmental awareness system. It requires the optimization of both the delivered data quality and the survey efficiency simultaneously. We are sampling a range of environmental conditions, temperature, wind, sky transparency. We are testing our survey strategy and the validation of the implementation using the feature-based scheduler, and we're exercising sustainable workflows. You heard a lot from other members of our team talking about, we can't be in this sort of all hands on deck continuous commissioning mode for 10 years. We have to shift into a mode where we can run in a predictable, stable manner every night for 10 years. Next slide. So this is a look at some of the performance from the science validation surveys. This particular data set here is one that we were looking at from early July that we used to claim achievement of the system first light technical milestone. We picked these nights because it was a period of relatively stable weather conditions during the Chilean winter. And so we were able to look at the distribution of the delivered image quality and the survey performance in terms of our rate of acquiring visits. What you can see here is color coding of the PSF full width half max that's been adjusted to zenith at 500 nanometers. And then the gray dots represent measurements of the basically estimates of the atmosphere seeing coming from our permanent dim. And so you can see there are many nights where we're tracking the atmosphere image quality, but there's also deviations. You can see that there's a spread on any given night and sometimes even within individual visits. Next slide. So this is a look at how one of the ways that we're estimating our system contribution to the delivered image quality. You can take just as a very simple model to consider the DIM as an estimate of the atmosphere seeing contribution, and then consider a quadrature sum model with our delivered image quality. And what we find is that while there is some scatter, there's a sort of general trend where if you consider 0.6 arc-second system contribution as being kind of a characteristic scale, you can see that when you add that in combination with the DIM and quadrature, then you get a distribution that approximately matches our delivered PSF4 with half max distribution. And the median is around 1.2 arc seconds. This is not as good as we would like it to be for the 10-year LSST survey, but it does show the sort of stable performance that has been achieved on the time scale of a week while running the SV surveys. Next slide, please. So what we observe is that there's when we look at this in detail, we see that the system contribution to the delivered image quality varies quite a bit. It can vary between nights, within a given night, and even across the focal plane. But we are achieving this sort of sustained system contribution at the level of around 0.6 arc seconds. Our design goal is to get that down to about 0.4 arc seconds. And we know that there are images that show that the system can do this. So if you look at the figure on the right, this is showing an image where across the full focal plane, you can see that the PSF4 with half max is around 0.6 arc seconds. And this has been achieved on several nights. We've been able to hold this kind of performance for about an hour or two at a time with some interruptions. I'll show some examples later. Next slide. Another aspect of the performance that we're looking at is the system availability. So if we look at that same data set of 8 nights where we were primarily running the SV surveys with pretty stable weather conditions, we can basically look at how often we're able to basically run the observatory in a continuous survey mode. So on the figure on the left, this is showing the distribution of time. Green is basically when we're running continuous science observations. Blue is some of the other testing that was done, including touching up the image quality with the AOS. And then on the right is showing basically the accounting of the time. If you go to the next slide, there's a summary of some of the numbers. Oh, unfortunately, it looks like somehow this got formatted a little bit funny. But what the key message to take away is that the rate of acquiring visits within the science program when we are running the SV survey is on pace to be able to run the LSST 10-year survey. Right now, if you take into account the various faults and our ability to recover from them, as David was just describing, we have about 85% system availability. If you include also the time when we are improving our AOS performance, it's about 75%. And if you include the total open shutter time, including some of the administrative controls that we currently have in place, it's about a little over 60%. Next slide, please. So this is a look at the system availability over the full LSSTCAM OnSky commissioning campaign to date. One of the things that you'll see is that we've had periods where we've really been focused on OnSky engineering. There's a period where we are concentrating on the observations for first look. There's been a number of periods where we've been off sky for up to a week due to weather. We are commissioning in winter in Chile. But what I'll call your attention to is that if you look to kind of the right side of the plot, you can see that there's periods basically starting in early July where we've had pretty stable performance running the SV surveys whenever the weather has been cooperative. And on those nights, we're typically achieving something like 700 science program visits per night. So we're able to achieve that steady performance now. Next slide. This is some pictures of what it looks like to be commissioning in winter in Chile. You can see frost and snow on the weather tower, covering the dome, covering the roads. Next slide. This is, again, what it looks like at the summit. We have another winter storm that's rolling in today. Next slide. So here's a look at the SV survey's progress. Next slide. So this is the SV survey's progress to date. This is up through the 29th of July. What you can see is that we've had several nights of closed dome testing in the past week because of adverse weather conditions. And so on the right, you can see that basically the rate at which we've been able to take visits for the SV surveys has fallen a little bit behind our simulations. You can also see that the slope matches on the nights where we have good weather conditions. So we know that the system is capable, but we're basically fighting against the weather in some cases. The mean number of visits per pointing right now is around 7 in R, I, and Z, and a little bit less in the other bands. So we're right at the cusp of being able to start building templates, but we haven't yet done this at scale yet. Next slide. These are just some links where you can find web pages that provide detailed reports of weekly and nightly summaries. Next slide. This is a slide that's mainly shown for reference, just to show you in the SV surveys are basically taking into account in the simulations our expected downtime. And then if you go to the next slide, this is showing a forecast of where we expect we would land at the end of the SV surveys in mid-September. So if you look at the curves that are shown in green and purple on the plot on the right, this is showing models where if you include engineering time, weather losses, and this is a very rough prediction, but maybe we would get something like 60 to 80% of the cumulative number of visits in the initial SV survey simulation that did not include weather losses. So this is maybe an estimate of where we would expect to land. Next slide. We'll skip this. This is reference material from the early science. Okay, next slide, please. So this is an example of where we are still in commissioning with Rubin Observatory. This is basically just a subset of all the diagnostic information that we have available on the system state. And so what we're doing is that we're constantly making correlations between all of our system telemetry and the delivered data quality. And then to get a sense of what this actually looks like in practice, if you go to the next slide, these are examples of basically, we're still commissioning. If you look on the left, this is an example of where we have delivered image quality at sub-arc second across the entire field of view, but then there's a change in the physical rotator angle, a change in the filter, and the image quality gets much worse. But then after running a few iterations of the AOS closed loop, it recovers. Next two slides are showing kind of similar examples of this, right? So this is basically where we're continuing to put our efforts. Okay, next slide. So the anticipated improvements to the consistency of the delivered image quality, we know that there are multiple aspects that are contributing to the image quality budget. Part of these are the dome louvers and the air ducts that are now being installed to better ventilate the dome environment. We are still optimizing the M1, M3 thermal control. There's going to be detailed discussion on this at the image quality sessions this afternoon. And we're continuing to optimize the AOS control loops. Next slide. So if you go to the next slide, this is just mainly for reference. There was a lot of discussion about the Cosmos observations in May, so I put in some quantitative details for those that are interested. Kevin, if you go to the one more slide, basically the median PSF full with half max across these Cosmos fields is between 1.1 and 1.3 arc seconds. Each one of these panels is showing one of the different bands, UGRIZY. Next slide. And then if you basically take into account the number of visits that are going into the COAD after basic cuts on the PSF with half max and transparency, it's something between 40 and up to over 100 visits per band. So this is comparable to the integrated exposure we would expect from 3 to 5 years of the LSST wide, fast, deep, just to give a sense. Next slide. All right, this is the summary. So I hope what you've taken away from this session is that we have a really outstanding, very dedicated, very disciplined team that has been working with outstanding commitment to solve these problems as they've been coming up during commissioning. The OnSky commissioning campaign is progressing nominally the way that we expected during the first 3 months. We've achieved the system first light technical milestone on schedule. We're working through all the usual types of challenges that are expected when you're commissioning a complex system. We're moving towards steady state operational workflows. And a way of thinking about this is that we're not just commissioning the hardware and software, we're also commissioning our team and being ready to run a survey for 10 years continuously. At this point, we haven't found any fundamental limitations that are limiting the LSST system performance during the first 3 months. We believe that the system is capable of delivering the LSST. That being said, commissioning is still ongoing. As a team, we are working the top priority issues to improve the system reliability. That includes characterizing, improving the delivered image quality. That's the AOS, the dome ventilation, the thermal control. We're optimizing our overall system reliability and uptime. And we have a pre-operations engineering and maintenance scheduled in September and October. I'll end there. Thank you.
Thanks, Keith. Keith, it's 5 minutes into lunch. People are disappearing. Keith can take messages on Slack. I'd like to thank the team that's actually making the data flow. So my thanks to them, and maybe we could thank all the speakers.